Okay, so we're going to take a look now at some of the reactions of acids and bases, which is the second to last section of the acid-base chapter. So a couple of these reactions we've actually seen already. You did at least one of them in lab a couple of weeks ago. So acids generally, they can react with different things, and they produce, or the products that they produce are going to be different as well. So for example, acids can react with metals to produce hydrogen gas. So in other words, they liberate hydrogen, and that was one of the reactions we did in lab. They can react with bases to produce salt, or a salt and water. And that's a general acid-base reaction, which we'll see in a second. And then acids can react with special types of bases that contain bicarbonate and carbonate ions in them to produce carbon dioxide in addition to a salt and water. All right, so we've used the word salt a couple times. Salt does not necessarily mean sodium chloride. All right, salt is just a general name for an ionic compound that doesn't have the proton as the cation or the hydroxide as the anion. All right, so those are some of the general reactions. We'll take a look at a couple specific ones here. So acids, we said, can react with metals, and they can be really reactive metals such as potassium, sodium, calcium, magnesium, aluminum, and zinc, which is the one that we actually did in lab. And we'll focus in on that reaction here. So this is the second one. And when you did this in lab, you had a zinc strip which you polished, and then you placed it in some hydrochloric acid, some HCl, and what you saw was a bunch of bubbles that were being produced, and those were bubbles of hydrogen. And if you remember, we tested those, or we tested the gas with a splint, and it gave the very characteristic pop or the squeak. Right, so in this case, the hydrogen was liberated, and you can think of this reaction as a single replacement, right? So the zinc comes in, it replaces hydrogen, hydrogen gets kicked out as a gas, and then the zinc combines with the chlorine to make zinc chloride, which is our salt in this case. Acids can also react with carbonates, as well as hydrogen carbonates, and in addition to producing a salt, some sort of a salt and water, we also get carbon dioxide gas. And this is also something that you did in lab a couple of weeks ago. So the second reaction here would be something similar to what we did in the laboratory. So we have our hydrochloric acid, and then we add some sodium bicarbonate to it. And by the way, sodium bicarbonate is just the chemical name for baking soda. And when these two things react, the sodium can come in, and it can take the place of hydrogen, and then the hydrogen takes the place of the sodium, right? So we end up making sodium chloride, and then the new combination that's made by combining the hydrogen with the bicarbonate actually quickly breaks down, and you get carbon dioxide, CO2, and you also get water, liquid water. And this CO2, again, would be responsible for the bubbles that you would see. And we can test that as well. And we did do that. We tested it with a splint, just a glowing, or a fire, in other words, a splint. And then we saw that it was able to put the splint out. So it extinguished the fire with no pop or squeak, as we saw with hydrogen. And then generally, and this is sort of the main thrust here of the acid-base chemistry, is acids can react with bases in what are known as neutralization reactions. All right, so if you think of an acid combining with a base, what we say is that they neutralize each other. So an acid neutralizes a base. And the typical products that we get when an acid neutralizes a base is going to be a salt, and then we also get water. So for example, you can also think of this as a double replacement. The sodium comes in, takes the place of hydrogen to make sodium chloride. The hydrogen now goes where the sodium was to make HOH, which is just water. Right, so this is our salt, and then we get water as our product. In essence, what we get is just salty water at the end. And when you look overall, what's happening in a neutralization reaction, really what's driving it is the H plus that the acid produces combined with the hydroxide that the base produces. Right, and then now we can make a little more sense of what's happening here. So the acid produces the H plus, the base produces the OH minus. These two things then combine to make water, right? And water, as you know, is neutral. And this is at the heart of every single acid-base neutralization reaction where the proton combines with the hydroxide to make water. And we can take advantage of this acid-base neutralization reaction in the laboratory to do an experiment called a titration, and that's how you pronounce that word, by the way. And all a titration is, it's the process of adding a base to an acid in order to neutralize it. And as a result of that, we can use the titration if we make some measurements in terms of the volumes that we used together with the concentrations of the base. For instance, we can calculate the concentration of the acid if we don't know what it is. Right, and that's really how it's so powerful. We're just using a normal chemical reaction, neutralization reaction, and the fact that acids and bases neutralize each other. We can make some careful measurements, and we can then calculate the concentration of either the acid or the base if we know the concentration of the other one. So a general acid-base titration is going to look like this. So in our setup, we have here, this is a burette, and in that burette we have our base, we have our NaOH, and we know its concentration. So NaOH of known concentration. And then in our Erlenmeyer flask down here, we have an acid of unknown concentration. Now, if we add enough base to that acid, we can eventually neutralize the acid with that base. So how do we know that the acid is going to be neutralized? Well, we're going to use an indicator, just like we used in lab, that told us the pH of the solution. And the most common indicator we use in acid-base titration is one called phenolphthalein, and that is added, and the color is going to change. That's going to identify the endpoint of the reaction, which is when we've added just enough base to neutralize all of the acid that was there. So phenolphthalein works very, very simply. In an acidic solution, it's colorless. And then in a basic solution, it's pink. So if we start off with some of the phenolphthalein in our acid solution down here, it's going to be colorless. And then as we slowly add enough of the base to the acid, we can monitor the color of the solution that's being formed. And once you see that pink first start to form, then we can stop the addition, and we know that all of the acid has been neutralized. So at the end point, our solution is going to be a slight pink color, and what that means is that the total number of moles of the base are going to be equal to the moles of the acid in that solution. We know what the concentration of the base is, and we know the volume that was used. We can measure the volume. And then from the acid, we know how much acid was used. We can calculate now the concentration using a little bit of stoichiometry. All right, that's now applied to a solution in this particular case. So let's take a look at an example of how to walk you through a typical titration calculation that involves stoichiometry applied to solutions. Okay, so here we have an example of how one of these problems could be posed to you. So it says in a titration, 25.0 milliliters of a 0.25 molar calcium hydroxide solution was required to completely neutralize 15.0 milliliters of HCl solution. And we need to calculate what is the concentration of the HCl. All right, so the first thing to realize here is that what essentially you're doing is you are performing a chemical reaction, right? You're adding the acid to the base, or I'm sorry, the base to the acid. So we can write an equation for that process. And it's an acid-base neutralization reaction. So we have our acid. So first, write the equation, not just write, but balance the equation. So we have HCl plus calcium hydroxide, CaOH2. All right, so we have an acid and a base, and we saw previously that an acid and a base combine to produce water, and then the salt. And what the salt is simply the calcium now taking the place of the hydrogen to make calcium chloride. All right, so this is a double replacement. Calcium chloride. Calcium has a charge of 2+, chloride has a charge of -1. So if we do our cross charge, we swap the charges for the subscripts, then we have CaCl2 as our salt. Right? So that's our basic or fundamental chemical equation that represents what's going to be happening in our titration. We need to balance it first before we do anything, right? Which you should do with every single equation. You want to make sure that it's balanced. So let's see. We have a total of 4 H's on the left side. We need 4 H's on the right. So we need a 2 in front of the H2O. That gives us 2 O's on the right. We have 2 O's on the left. We have 1 calcium on the left, 1 calcium on the right. We have 2 chlorines on the left side. We need 2 chlorines. 2 chlorines on the right. We need 2 chlorines on the left. So we can put a 2 in front of there. And we end up with our balanced equation. Okay, so once we have our balanced equation, then we can go ahead and make some sense of the numbers that were provided. All right, and you want to start with the thing that you're given the most information about, which in this case is the calcium hydroxide. We're told that we have 25 milliliters of it. That's how much we used, and we know its concentration. Right, so remember the concentration, molar or molarity means moles per liter. So for the calcium hydroxide, we're told that we have 25.0 mils that was used, and we were told that it was a 2 or 0.25 molar. Right, so remember this would mean that we have 0.25 moles of the calcium hydroxide for every liter that's present. Well, did we use a liter in the titration? No, we only used 25.0 mils, right? So we can convert that to the same unit that we have in our molarity, and all we need to do is just divide by 1,000. So we end up with 0.0250 liters of our solution. All right, so we have a volume of our calcium hydroxide. We have a concentration of our calcium hydroxide. we can then use those two things to get to moles of calcium hydroxide. Now we did that in class a couple times. We were able to see how we can use the volume times the concentration to get to moles of calcium hydroxide. So it's important to get to moles because the balanced equation gives you that mole to mole ratio. Right? And we said this multiple times in class. Getting to moles kind of opens up the equation for us. So let's take a look and see how we can do that. So we start with what's given. We have our 0.0250 liters of the calcium hydroxide. We're going to multiply it by our concentration, so 0.25 moles of calcium hydroxide per liter. Right, that's our concentration. We just turned it into the proper units, moles per liters. So we can see now the liters cancel out, and we're at moles of calcium hydroxide. We need to find something. We need to find the concentration of the HCl. Right, so what relates the calcium hydroxide to the HCl? Well, that's your mole to mole ratio from the balanced equation. So from that equation, we can see that 1 mole of calcium hydroxide react with 2 moles of HCl. Right, we just get that from our balanced equation. So we put it this way so that the moles of calcium hydroxide can cancel out over here. So up to this point, we have moles of HCl. What is it that we needed to find? We needed to find the concentration of HCl. And remember, the concentration in square brackets means moles of HCl per liter of solution, right? So up to this point here, we've just found the moles of hydrochloric acid. We then need to divide it by the liters. Well, do we know how many liters of HCl was used? No, but we know how many mils were used, 15.0 milliliters. We can convert that to liters. We simply divide by 1,000, and that's 0.0150 liters of our HCl solution. And we can just stick that right in here, and we can just divide it, right? Which is the same as multiplying by 1 over our volume. So up to this point, we can see that all of our units cancel away, right? The liters of calcium hydroxide cancel down here as we use the volume and the concentration. Then the moles of calcium hydroxide cancel here as we use the mole to mole ratio. And the only units that we end up with now are moles of HCl divided by liters, which is molarity. So all that's left to do would be to crunch our numbers using our calculator. Okay, so if we use our calculator, we plug our numbers in, we end up with a value of 0.833 molar HCl. Let's double check here that we have the right number of sig figs. So let's see, 3 sig figs, 2 sig figs, 3 sig figs. So final answer then can only have 2 significant figures. So it'll be 0.083 molar HCl. Right, so what we've done here is we've combined several concepts in this problem. The first thing is we use what we just learned, the fact that acids and bases react in a neutralization reaction to produce water and a salt, and we balance that equation, right, which we've done in the previous couple chapters. And then we used what we learned from chapter 9 in terms of our solutions, how we can use the volume and the concentration to get to the number of moles. Then we use the mole to mole ratio from the balance equation to convert to moles of something else, and then we can calculate the concentration of that new thing by simply dividing by the volume in liters.